All right. Welcome everyone to, oh, nope, admin
wow. Just admitting everyone, yes. So trickle in.
Yes, so welcome everyone. Duncan, do you want to start sharing your screen? Because we have a packed agenda. So we're gonna let your screen to be shared first. Welcome everyone to our hackathon showcase session. And for this workshop, pre-workshop, we had a blast working with 150 people before this workshop, doing a hackathon competition on 3 topics in collaboration with Climate Informatics community, where Claire from the CU Boulder is also joining us here right now, who started a community. So this hackathon has 3 topics in collaboration with 3 groups. The first topic is climate bench or climate emulation in collaboration with Duncan Watson-Paris from University of Oxford. And we have collaboration with Earth Lab from CU Boulder, Natasha Star Wars on the wildfire risk. And we also have a topic on marine heat wave in collaboration with Hilary Scannell from Columbia University. So we're gonna invite the team to showcase their result this time. And we want to invite the collaborator to share an overview of the topic first. And we also invite the HPCC and the team from the HPCC hackathon in collaboration with with NVIDIA today. So we have a packed agenda, and Duncan, please take it away for the climate bench topic first.
Brilliant. Thank you very much, Douglas. Yes, I wanted to just provide a quick kind of reminder for maybe some of those who saw the hackathon at the start of last week now, and introduce it briefly to those of you who hadn't come across it. So the basic idea is that within CMIP6, as part of the scenario MIP activities, a number of climate models from around the world simulated a number of different future scenarios spanning a range of different climate forcings into the future, some quite strong and some with higher mitigation, so less forcing or less warming in the future, but also with a variety of different policies in terms of short-lived climate forces and air quality. But the scenarios which span this space are quite sparse. So there were the 5 kind of core scenarios and a couple of other optional ones. And what we'd like to do is develop a tool or a benchmark set of data and models to be able to interpolate between these different scenarios for the range of different climate forces, including well-mixed greenhouse gases and short-lived forces such as aerosol, in order to be able to emulate maps of temperature and precipitation for these different forces. And we wanted to go beyond kind of mean temperature, which I think has been looked at quite a lot. Even maps of temperature has been looked at a little bit, but really looking at some of the nonlinear responses, particularly with respect to precipitation. So the task was to estimate one of the we held back one of the scenarios from the teams for training. So this particular scenario, SSP 245, which is sort of a middle of the road scenario, which nevertheless leads to quite dramatic warming, particularly in the Northern Hemisphere. And we asked the teams to emulate annual mean temperature maps, the diurnal range in temperature, which is an important health measure variable and is sensitive to aerosol, as well as annual mean precipitation and some of the tail of the precipitation. So looking at the something that demonstrates the extremes of that. It says here that this is ranked by RMSE for 2050 and 2100. In actual fact, we tweaked that, and so that's actually the RMSE over the whole period that this scenario is run, so from 2015 through to 2100. We provided a very simple baseline model. For reference, I included here the difference between the NOAA ESM model, which we used here for the training, and another important global climate model, UK ESM. And the RMSE over this scenario for UKSM to the NOAA ESM data that the teams are trying to aim for is 1.8 degrees in the mean temperature and 1.2 in the temperature range, 0.8 in the precipitation, 2.4 in the extreme precip. So if it's a lot of numbers to take in, but if you can bear those numbers in mind when you hear from the teams, then hopefully I think it demonstrates a nice level of skill in what the teams have managed to achieve. With that, hand back to you, Douglas. I'm not sure if you want to do the next teams or do the presentations now.
Thanks, Duncan. And can you stop sharing? And we have two teams, two leading teams for this topic, which the first one is Bench Cloudies, and will be presented by Paula Harder as well as Kai Jagler. And Paula and Jagler, please go ahead.
Okay, yep. Hi, here's Kai. Paula unfortunately couldn't make it. She had a little car problem, but I will present alone today. Thanks. So exactly. We are the Benched Cloudies. Maybe you can go to the next slide. Yeah, here just a quick overview of who were the members of the team. So we have Paula Harder from Fraunhofer. She has a background in computer science. And then we have Maura and Theodore, which are both more from the atmospheric science domain, both from Stockholm University, and myself also more tech background. And I'm doing a PhD at ETH Zurich. And Maura, Theodore, and me, we are also part of the eMiracli program, which is also Duncan is the program coordinator, where we look into improving aerosol cloud interactions with machine learning. Exactly. You can go to the next slide. Yeah, just this reminder what you want to do, what Duncan just showed. So basically you want to build an emulator of the CMIP6. And our goal is to kind of predict this dashed line that we see here, the SSP 245 scenario, based on the greenhouse gases and the aerosols. And yeah, continue to the next slide. Exactly. So our strategy was, like often in hackathons, you kind of all work on the same model or something, but we said, okay, maybe just try out different models. So we had kind of split into three. Maura and Theodore were working on Gaussian processes. And yeah, why we divided in three is because different models have different pros and cons. And pro of the Gaussian process is that it's non-parametric and it quantifies also the uncertainty quite well. But it can be difficult to tune the kernel. But as we saw with Duncan's baseline model, that it can actually achieve already quite good results. Then Paula looked into a unit architecture. So this is basically a convolutional neural network architecture where we have an encoder decoder. And the pro of this is that it incorporates the spatial relationships. So basically this frames the problem as a computer vision problem, where we, instead of the RGB channels that we usually have in computer vision, we take the different inputs, the aerosols and the greenhouse gases, as different channels in the input, and in the output, the different channels are the temperature, precipitation, and so on. But here the problem is a bit that the training data set is not so big, and usually neural networks need quite large data sets to be efficient or to perform at their best. And then I tried out the gradient boosted decision trees. This is kind of a proven method in machine learning competitions, especially for tabular data. The problem here is also, like the Gaussian processes, it's like point predictions. So we don't really take into account the spatial covariates. So we try to predict from one grid cell to the other, but not taking into account the spatial covariates. Also, none of our approaches, we kind of capitalized on the temporal or like a time series, which could be done in the future as well. But yeah, to our surprise, actually, the gradient boost decision trees, they performed the best, better than the unit apparently, and apparently also better than the models of the other teams. So if you can go to the next slide, you can see the results. Yeah. So yeah, maybe I should have plotted the grid lines of the continents, but yeah, on the left side, we can always see the CMIP6, so kind of the ground truth. On the right side, the emulator. And yeah, we see that picks up the trends quite well, but also that especially here, if we look more into like the 2100, that there is still quite some differences. Especially if we look, for example, for diurnal temperature range there in the high latitudes, the signal is not really there, but nonetheless we get reasonable emulator, but I would say there's still a lot of room for improvement, considering that we here only do point-to-point predictions and not taking into account the temporal development. Yeah, we can definitely do this in the future. Yeah, was there a question or? I think just someone sneezed. Okay, then
Yeah,
then we can go to the next slide. So for precipitation, which is usually harder to predict than temperature, and which also can be seen here. So in the emulator, again, like in the right side, we can see like the big signal there in the tropics. But yeah, it's also, I would say it picks up the main signals, but especially also for 2100, there is still quite a lot of improvement to be done. Nonetheless, we get a reasonable emulator. So this is mainly the results, the visual results. And so we just have like the main challenges now. It was like also deciding, okay, which model we should try out, because we had many ideas. Also, we still have many ideas, but once you kind of commit on something, it's hard to pivot from this in like a 3 or 4 day hackathon. Also, I was really surprised that this boost decision trees of the grid cell to grid cell prediction were the best performing model compared to, for example, the UNET. But maybe here the data set is quite too small and we would need a larger data set, because here also the usual, like in computer vision, we often use this data augmentation techniques. We just like rotate an image or kind of leave something out, but this doesn't really work here in this case because it would be just unphysical, I guess. And what I would really like to try out is to maybe use a model that also takes into account the temporal covariates, which could be done with a LSTM, for example. And also it could be interesting to try out the transformer architecture. I'm not sure how the audience is familiar with this, but this is kind of the new boss in town, I said, for natural language prediction and also computer vision. And I thought it could be very interesting to try this also out for the emulator. However, this is even more data hungry, and I'm not sure if we can, if the data set is large enough for a transformer. Yep, so this was it from our team.
Great, thanks, Kai. And do we have any questions for the team of Bench Cloudies? First of all, I really want to say I'm really impressed with all the creative names that all the teams have been coming up with. And I will share the team names with everyone like later. Okay, if not, because we have a packed schedule, we're going to move on to our next team on the climate bench topic, which is emulate team, or I don't really know how to pronounce it, but as you can see, it's really creative. Like Lucille and Emily, can you go ahead to present the results?
Yes, so I'm Emily, and together with Carla Rush and Lucille Rica, we were emulating, so the right pronunciation, I guess. We are also, all three of us are part of the iMiracle as well. And unfortunately, none of us had a machine learning background, so we were kind of just trying things out in this challenge, which proved quite interesting for us. I think we learned a lot. And it was quite helpful to have Duncan's collab notebook to start with, because it gave us a few ideas. If you want to move to the next slide, I can describe. So there are some title slides. The slide titles are missing, but here, so the problem, we really started by trying to think of what we as climate scientists could bring to the table for this challenge. And we thought there is a few important things. So the first one would be to capture spatial patterns because, well, apparently Kai just said that the pixel by pixel prediction was quite good, but we thought this was probably too simple of an approach. So we wanted to be able to capture these spatial patterns. And in Duncan's notebook, we saw that this was done with the EOF reduction. And we tried another approach, which I'm going to talk about a bit later. And then we also thought that it would be interesting to capture the temporal evolution, because especially, for instance, if you think of greenhouse gases, to know the concentration or the emission of greenhouse gases at one given time step is not enough to determine the temperature at this given time step, because the greenhouse gases are going to stay for a really long time in the atmosphere. And so you need to kind of know the historical emissions. So that was our basis to start thinking of the model. And you can move on to the next slide. Yes, so there used to be an animation on this slide, but I didn't know this was going to be a PDF. So we got inspiration from this article that I just featured on the slide, how to work with time distributed data in a neural network. So the first step of our model was a convolutional neural network to be able to extract the feature in the different emission variables. So those are especially important for black carbon and SO2 because there's no spatial feature for the greenhouse gases in the data. And then we fed that spatial features to an LSTM. So the model that Kai just mentioned, actually, that is able to look at temporal evolution. So LSTM stands for long short-term memory, and it's an example of recurrent neural network. And then there's a dense layer and a reshape layer to reshape everything into the format of maps of temperature and precipitation. Yeah, so that was the approach. But as I said, I've never done that kind of things. And so I just tried out an architecture and then I wasn't really able to optimize it because I didn't have enough time. So I guess the results can still be improved, especially also if we have more data, but I can show you the results that we got. We trained on the 3 simulation, 126, 370, and 585. We left out 370 low NTF, which was another part of the data set because it didn't have the right number of time steps that we wanted. And the results for temperature are going to be on the next slide. And I think what's interesting, so the predictions were a bit disappointing, I think. But what's interesting is that the prediction skill increases with time. So like we get a better prediction in 2100 than we get for the earliest year. So I think that's probably because we took temporal evolution into account, but that's an interesting feature. And yeah, probably can be improved if we have more data. So that's for the temperature. And on the next slide is also going to be the diurnal temperature range. And for this one, I also actually included the predicted temperature as a predictor for the diurnal temperature range because I wanted to see if it had an influence, and turns out it improves the prediction by 0.1 RMSE points. So yeah, and then I tried the same approach for precipitation. It wasn't as good. And Lucille was able to obtain better scores with a simpler approach. So she's gonna present the next few slides.
Thanks, Emily. So hi, everyone. And indeed, aside of training a neural network, we also try to find like good combination of kernel function for Gaussian processes, but we were not able to find the optimized solution. And finally, it turns out that a simple random forest model gave us like nice results. So we just use the basic random forest implemented in scikit-learn, and we just trained the random forests with the combination of the historical input with the SSP 5.85, and we also just kept like in the baseline model, the first principal components for the SO2 and BC emission. And finally, it gave us so pretty good results. So of course, the prediction will get worse with the time, but the advantage, I think, of random forest is that because we are doing a binary partition on the training data, at the end, the prediction is an average of all the prediction, and you cannot have like an extrapolation of the training data. And comparing to the gradient boosted decision tree that Kai presented earlier, random forests will just do the final prediction at the end by averaging at the end the trees. And so it's another solution that gradient boosted decision trees. So if you can go to the next slide, you will see the result for the precipitation. So as I said, with time, the prediction gets worse, but results are still nice for 2050, for example. And what we saw on the validation plot, for example, is that random forest output prediction will be in a narrow range, so values will not be so, the spread will not be so high. So it gives nice result for precipitation, but for example, for the extreme precipitation, if you go next slide, it will have some limitation because finally the extreme values are less well predicted. So of course, we should have tuned the random forests or tried with a combination of the different social pathway. But yes, it's just a useful reminder that sometimes trying with a simple model, it's always a nice idea to see that in middle term prediction, it gives us still good RMSE values.
Great. Thanks, Emily and Lucille. And I would like to invite everyone to ask questions in the chat. And also we will have this discussion again in the Slack channel. So if you are in the Slack, please ask questions to our presenters as well. And I would like to move on to our next topic. And one more time, this hackathon is open, so everyone can still try to talk about this topic and email Duncan about this topic. I'm sure he will be really happy to work with people to move this into a publishable result in the future. So please continue this. And we want to use this hackathon as a way to form the collaboration and for people to learn about new topics and new models for this purpose. And next, I want to call on Natasha Stratwas from Earth Lab at CU Boulder. Natasha, are you there? Do the recording?
Yes.
Yeah, please. Natasha, yes, go ahead. Please give your 5-minute elevator speech for the wildfire risk prediction topic and why we choose that.
Okay, hold on 1 second. I'm just getting the, I'm pulling up a PowerPoint, which I think like this visual will be very helpful. Hold on 1 sec. Zoom disappeared, hold on. Share.
While we're waiting, I want to give another shout out to Claire Montiloni from the CU Boulder, who started the entire climate informatics community in 2011, if I remember correctly. And she is the one who are making this whole collaboration possible and who introduced us to Natasha and at Earth Lab. Thanks, Claire.
So can you
Amazing.
see the,
Congrats.
Thanks. Yeah, we can see your slides, Natasha.
okay, are you seeing the right view or are you seeing just the right view? You see it in big form?
Yes.
Okay. So the fire risk hackathon kind of came about because 2020 was a really devastating year. It was very extreme. And we've just had one devastating extreme year after another. And, you know, work has been done to project the hazard of extreme events. Actually, I was the first person to do that back in 2013. And when we're talking about hazard, we're kind of talking down here when you're looking at this place in orange, when you're talking about the hazard of fire. And that's really thinking about climate and the weather conditions that make fuel flammable. It's considering the amount of vegetation that you have and then the potential for lightning ignitions like lightning. And so there's actually been quite a bit of work done on the hazards of fire and predicting extreme fire events going forward across the West under a changing climate. But really, one of the things that's actually inhibiting us from taking actions, both with policy and with, let's say, businesses and companies like power companies for making changes to the way that they do things, is this translation of hazard or the potential that something could happen to the actual risk posture that they have, because that's really how businesses operate and how policymakers operate, is that when the risk exceeds a certain amount, then they're more likely to make changes. And so as you can see here, that while there's been a lot of work in this foundation around hazards, there's been less work around vulnerability and exposure, which are the integration of our consideration of social systems and our built environment or our technological systems like power lines and power infrastructure. And so this particular project or hackathon topic was around this idea, and it was kind of building off of a paper from Iglesias et al. It says down here in prep, but actually Virginia Iglesias actually just published a paper this year called Risky Development, which sets up the foundation for this framework for how we combine demographic information and development scenarios to start looking at risk. And so this particular project was using development scenario, high resolution development scenarios developed out of CU Boulder with climate data and fuels to help us predict fire risk. And so the models were all trained and developed from 2000 to 2014. And then the assessment was actually looking to see how well we did in an extreme year of 2020. So I think that that's really important as we keep that in mind and we see the results, that this was actually a really big challenge, because it not only looked at climate forecasting and hazard forecasting, which kind of has been very well established in the literature, but how do we bring the social and the human component into it? And then on top of that, you know, considering, can we predict an extreme year? So that's the overview, and I'm excited to see what the different teams have to show.
Thanks, Natasha. And with that being said, I'm going to invite the wildfire risk winning team, which is Seeking Trees on Fire. And I would like to also invite them to share how they came up with this name. Go ahead, Eva.
All right, thanks, Douglas. Yeah, so I will present the results of our wildfire risk prediction. Our team was named Seeking Trees on Fire, combination of our
you
first...
become muted, so did something happen on your end?
I can still hear
Really?
you. It might be you, Douglas.
I could hear her, Doug.
We could hear.
It's my problem, sorry.
Okay, well, can you go to the next slide, please? Yeah, perfect. Okay, so yeah, so we all have different backgrounds. We're all pretty much distributed around the world, and we've all worked, I think, on climate hazards, on weather hazards, if it's precipitation, if it's fog, but none of us really worked on fire before. So it was kind of like the motivation to, I think, try out something new, but we all do have experience with machine learning. And one method that we've all worked with before is random forest or just tree-based models. So this is also the reason why the tree is in our team name. So next slide, please. Okay, so we've all already heard the quick introduction to this hackathon topic, and the goal here was, if I cite the description real quick, to develop a data-driven method to predict the risk of the local community to wildfire. And we had climatic and wildfire specific and topographic data to model the total number of destroyed and damaged structures, so buildings. So the training data were wildfire incident reports from 2000 to 2014, and the test data was from 2015 on. So next slide, please. Yeah, so our strategy in this hackathon was first looking at the data and also preparing it for the model, and then we went into model training, and we've decided, well, we had two predictants to model, so we decided to have one model for each parameter, and we tested different machine learning methods, and those were random forest, XGBoost, and deep neural networks. And the XGBoost actually performed best during our training, and this is why we've then chosen it. And we've also did some hyperparameter tuning. We did random search CD for the XGBoost. And yeah, then we applied the model to the test data. So next slide, please. So when we looked at the data, we saw, as you can also see in the really simple plots on the right-hand side, that the distribution of the data was really uneven, and there were a lot of small values, both for total structures destroyed and damaged. So we did try to actually use data transformation when we used the CNN model, but this didn't improve the model. We had a couple of, predictors that we could choose from, as I've already mentioned. So some fire variables, for example, the burned area, the fire spread rate, and a maximum daily growth in burn area. There were some location variables such as latitude and longitude, for example, and also the height above sea level, and also some climate variables, which, for example, maximum, minimum temperature, precipitation, surface downwelling, radiation, and wind, and specific humidity. And with the climate data, we've decided to calculate for all those climate variables, to calculate the mean, the minimum, and the maximum of those variables in the time period that the fire was actually burning. We've had some missing climate data for some fires, and for those fires, we also didn't have any location data. So our first choice would have been to kind of take the closest fire and use the climate data from that, but that wasn't possible. So we just used for those fires the mean for the state that they were in, which we know isn't a really good proxy, but for us it was better than using no climate data for those fires. So next slide, please. So yeah, our model training did actually kind of, like, all the models were similar, but as I said before, the XGBoost did best with RMSE of the total structure damage of 9 and of the total structure destroyed of 123. So yeah, just keep in mind those numbers when you see the result later. It's going to be interesting. And what I really like about those tree-based models is that you can also look at the the model itself, like which features were important. And I had a quick look at the feature importance. And for both those separate models, the burn area in square kilometers and also the sum of the property records, of the build-up property records within the fire perimeter, they were the most important features, and as well as the fire spread rate. Concerning the climate features that we've used, the maximum of the eastward wind was quite important, as well as the sum of the precipitation. So yeah, next slide, please. Yeah, so this is just a screenshot from our GitHub result page. So you can see that the RMSE went up pretty high, both for the prediction of damaged structure and also of destroyed structure. And this was actually the case for all teams. So we're still really close together with the prediction errors. So I think there's room for a lot of improvement, and this is actually bringing me to the last slide of challenges and ideas. So we only had the climate data for fire incidents for the year of the incident, and we thought that maybe it would also be good to kind of calculate climate features which show the development of some variables, for example, precipitation sum of like the 6 months before the event, stuff like that. So this would have been quite nice. So for like ideas for the future wishes would be to have more climate data. And as I've said before, there was also missing climate data for some fire events and missing location information, and also the number of observations were quite low, so less than 2,000. And we also would have wished for maybe building location data and to kind of like combine this and compute the risk on each building. And we also thought that we could maybe couple those models to train one model with the output of the other, for example. So yeah, so that's it from my side. Yeah, I can take any questions if you have some.
I have a quick question. So, you know, it's nice to see the RMSE, but it's really hard to interpret the RMSE without kind of an understanding of it in the context of the accuracy or the total predicted. Do you have a sense of sort of the normalized RMSE against that or anything like that?
We don't have the actual observations, so we couldn't calculate that. I don't know if that would be possible, like afterwards now. I
guess I was thinking not from the 2020 year, because that data still hasn't been published, but I was thinking from like when you trained, from the years when you did have more of that data. Do you have a sense of like where you were? I mean, obviously 2020 is an extreme year. So it was really putting your models to the test. It's kind of an interesting experiment, but I was just wondering on the training data.
I mean, what we actually also did was we kind of trained on 90% of our training data, and then had like a quick validation look at the other 10%. And there the difference was already quite high. So like with the 90%, we had, I think, I don't know, an RMSE of 1 maybe. And then for the other 10%, we had one of, I think 9 point something, what I showed before. So I think this is already quite a lot of overfitting in that first step. Yeah, so, and I also think that, like, I didn't take a closer look at the distribution, but considering that we have so many values which are really low for the total structure damaged and also destroyed, this is, I think, quite I would say it's not so good yet, the model. Yeah.
Yeah, this is a really like cutting edge challenge, but it's the question that industry's been asking. So yeah, thank you so much. This is really interesting.
Thanks, Natasha. I just realized I was muted when I was trying to ask people if they have any questions, but thanks for filling in to ask the questions, Natasha. And we already have other questions in the Slack. So if you can go in there to answer the questions in Slack, Eva, that would be great. Much appreciated. And also I know it's like dark at nighttime for you. So thank you for joining us right now. And with that, I want to switch the gear a little bit more from the land to the ocean. So I want to invite Hilary Scannell from Columbia University to share about the marine heat wave topic that we have been doing for this hackathon. Hilary, take away.
All right, thank you. Can you hear me and see my slide?
Perfect.
All right, awesome. Hi, everyone. So the last the hackathon topic was about marine heat waves, and using all the data we have and what we know about what drives marine heat waves, can we predict their occurrence? So this is just one example here that I'm showing you. This is a marine heat wave in the Northeast Pacific, so off the coast of the US West Coast. And this happened, this image is from May 2015. And so this was an enormous marine heat wave that persisted for multiple years. And it caused a lot of impacts to the West Coast. So when you have warm water in the ocean, it drives down the productivity. And so what that means is there's less fish and phytoplankton for other marine animals or fish species to feed on. And so what we were seeing was a mass die-off of seabirds. We were seeing sea lions that weren't getting enough food to feed their pups, so they were starving. And we also saw a massive harmful algal bloom just from this event. And so that led to a lot of toxic algae accumulating throughout the food web. And that toxic algae can actually cause paralytic shellfish poisoning. And if that's ingested into humans, it can be very bad for the fisheries and the economy. And so there's a really a big need right now to try to understand and forecast these marine heat waves, so particularly when and where they're going to occur. And the main reason why we want to forecast these events is that we can warn the management, the fishery managers, to either change their fishing season, to put other measures in place that kind of alleviate some of the other stressors on their marine ecosystem so that they're better able to take the brunt of these warming events. And so that's kind of the motivation for why we want to predict marine heat waves. These events occur all over the world. What we've found is that they're mainly driven by the atmosphere, although the ocean can play a very important role. But you're just looking at the scale of this massive marine heat wave, and that's usually caused because there's a reduction in wind speed, there's increased shortwave radiation hitting the sea surface. And so that upper part of the ocean, we measure the sea surface temperature, and that's how we define these marine heat waves. That can, those atmospheric conditions can then cause a marine heat wave at the sea surface. And so what we've included in this hackathon are some very relevant atmospheric variables. And these variables are actually taken from a blend of both in situ measurements and reanalysis data. What you find in a lot of these products is that some of the data might come from satellites, and that mission might end, say, so that happened in the OA flux data that we used. We took the shortwave radiation and long wave radiation. And so at the end of 2009, that satellite mission ended. And so you kind of have to fill in the gaps with the data. And so that was one of the challenges that I'm interested to hear how the participants kind of managed. But we have atmospheric variables such as the long wave radiation, short wave radiation, and then the turbulent heat flux, that's sensible and latent heat flux. And then the atmospheric temperature at 10 or 2 meters, I think, and then the wind speed at 10 meters. So all of these are very important, we think, in being able to look at the relationships between those variables and the occurrence of marine heat waves. And there's a lot of data here. And so we're looking at monthly variables starting in 1981 in September, going through present. And it's a global grid, and it's 1 degree horizontal resolution. So there's a ton of data. And so the idea is that if we can use this data and build a machine learning model, we can get some really interesting, we can learn some interactions between these features that would help us predict these marine heat wave events. And I'm very excited to see what this group has found, and I'll stop there.
Thanks, Hillary. And like Hillary said, like wrangling the data is always the most challenging part to make sure that our audience, our participants can use the data. So I'm gonna share the screen and inviting George Cutter from Fisheries, as well as Jin Lim to join us for sharing their results.
Okay, thank you, Douglas. Our team worked on the marine heat wave prediction problem, and the team name was JAM and G, gotten from the first letters of all of our names. Next, please. So the team was composed of Jin Lim from NOAA's Atlantic Oceanographic and Meteorological Laboratory, and Ayush Prasad from SMIT in India, Meng Zhu from University of Connecticut, and myself, George Cutter from NOAA Southwest Fisheries Antarctic Division. We all work on a variety of things that are distributed around the world and have various levels of background in machine learning and AI. Okay. So marine heat waves are characterized by very warm regional sea surface temperatures, as Hillary Scannell just described. And these events are increasing in frequency, and they threaten the ocean ecosystems. And being from NOAA, we should all be familiar that ocean ecosystems support human food resources and activities. Therefore, we need to predict and detect marine heat waves in order to enable early warning systems and to mitigate these. So the project problem was basically to predict the onset of these marine heat waves using the air-sea flux data provided by the Hackathon datasets. Next. The data for training our models was the OA flux dataset, and OA flux, ARC fluxes trained contained 26 million rows and 10 columns of data, plus latitude, longitude, and time for each row. The prediction, the labels, which represented the marine heat wave events, were about 100 megabyte file. I'm not sure how many rows, but they represented a binary classification for each cell on whether it was a representative marine heat wave condition or not. Next. Those millions of rows in the data sets converted to spatial coverages from about 400 monthly periods between 1981 and 2015. And on the right, the upper level, you'll see examples of the evaporation data variable from the OA flux data set from the first time period and the last time period on the left and right. And in the lower, you'll see the labeled marine heat wave events representations for those same monthly periods, 1981, 2015, and the yellow in the lower figures indicating positive presence of a marine heat wave, and the blues being none. And there are also the land masses represented in terms of zeros as well. Okay.
So one thing that we noticed when we were looking at the data was that there were a lot of missing data in the training set. So like almost half of the data was missing. So some of the rows had entirely NA values and some of them were partially missing. So we were trying to think of different strategies to actually deal with all these missing values. So one way is to just use the missing data values as they are without any changes. And we also tried to create rolling seasonal average of monthly data. So we tried to like get the mean from data from 2 months, 3 months, and 6 months. And another thing we also tried to do is to try to fill in missing data columns with the mean of that column, or with whatever value that comes directly after that row in the same column. And another thing that we also tried is to drop the missing values. And besides dealing with the data, we are also trying to look for suitable models for this binary prediction problem. So we tried to use XGBoost, which in our case performed the best. So the advantage of XGBoost for this particular problem is that it supports missing values by default. So you don't have to replace the missing values with something else, or you don't have to drop the rows with missing values. We also tried using support vector machine. So that's like a totally different approach, which is not based on a tree. And the support vector machine function that we used was a SGD classifier. So that is based on a stochastic gradient descent. And when we tried using the support vector machine, most of the predictions came out to be negative. So all the output variables were zeros. And probably that's because the labels in the training data set are not balanced. So I think most of them are zeros and only a few of them are 1. And probably the parameters were not optimized. We also tried using a neural network model with an Adam optimizer. And we tried to optimize it based on the binary cross entropy. And that model itself also produced mostly negative, actually all negative or zero predictions. And that could also be because the model is not optimized, or maybe we tried to use a ReLU activation function, and maybe that's not the most suitable optimization function to use, activation function to use. So next slide, please. So as I mentioned, the best scoring model for this hackathon was the XGBoost model. So for this model, this is based on data 1 month prior. So we didn't use any mean of like different month intervals, and we actually used the NA values as they are. So what we did is we also noticed that the input variables had like different ranges. So we tried to use a standard scaler to like scale the input variables so that they are within similar ranges. So the standard scaler actually scales the data based on the mean and the standard deviation. And these are the parameters that we use for the XGBoost model. So yeah. And I don't think this is the best model, but we didn't really have the time and computing power to actually optimize this model. So next slide, please. So what were the challenges? So the challenges of this hackathon was that the labels in the training and testing sets are likely highly imbalanced. So most of the labels were negative, zeros, and there are small proportion of positive predictions, and that could be affecting the results of the support vector machine and maybe the neural network results. And in the future, maybe we have to look into strategies to better balance the labels in the data set. So I looked up some of the possible strategies, and this include like, undersampling the majority label, copy rows of data with minority labels, or we could actually create synthetic data to kind of try to increase the number of rows of for the positive, the minority labels. And also this data set is quite huge, and it requires a lot of computing power to actually analyze and create models for this data. So we tried to use Colab at first, but that kept on crashing. So we had to try different platforms. And because of that, the parameters for all of the models that we tested are not optimized. So ideally we would like to do like a grid search or a randomized search with like cross validation. But when I tried to run this, it takes like more than a few hours to run, and we only have like a few days in the hackathon. So we didn't really get to optimize the hyperparameters for all of the models that we tested. Next slide. So during the hackathon, our priority was just to actually be able to create predictions to submit. So like some of us were working with NOAA, and we also had errors working with Colab. So mainly Colab doesn't support data from the NOAA's Google Drive due to security policies, and that was pretty demotivating because we have to host our data somewhere else on our private accounts. And the first 2 days, we actually spent most of the days trying to actually find an alternative platform besides Google Colab, because that kept on crashing. So each of us actually had our own way to make the code and data work together. So I started using Amazon Cloud because I have an account over there, and George used his own local computer to run these predictions. And these recommendations are from George, actually. So he actually suggested that maybe we can have the problem statements 1 week before the hackathon, so that we can try to like test out the platforms and download the data, and then we can identify and fix architecture related problems. And we can put more into effort instead of like spending a lot of our time trying to like get the code and data to work. Maybe you can spend more time with the models and with the data. And one good thing that came out from this hackathon, among many other good things, is that we got to know like-minded people, and we hope to continue collaborating with each other to help develop machine learning approaches for our own research problems. And if we have time, we can examine this heat wave data in more detail to actually look at the importance of the different predictive variables. Hopefully we can test other models or try to optimize the current models that we have. And I think that's all we have for the presentation.
Thanks, Jim, and thanks, George. I think those are really good recommendations, and we realized that in the process of this, the hackathon, the Colab is not necessarily working very well for some participants. So we appreciate the feedback, and we will be working to improve that. And hopefully we can continue the conversation with you to move this marine heat wave. I know Hillary is really interested in this topic. We're going to move forward with this topic with you all together. And thanks again for sharing these results. And I'm going to share the thanks to all the groups who participated in this workshop hackathon. And I'm going to actually slightly switch the gear to another hackathon event hosted by NOAA, which is the High Performance Computing Program. Bill and Frank, are you here? And in collaboration with NVIDIA? Frank, can you speak?
Sorry, I was muted.
Yeah.
Can you hear me now?
Yes, great.
Okay. And can you see the slides?
Perfect.
Okay. All right. So I'm not Bill Cushman. I think he was the original one slated to speak today. My name is Frank Indiviglio. I'm the Deputy Director for High Performance Computing. Bill Cushman is the person who coordinates hackathons in the program for the HPCC program. Let me turn this on to, excuse me. And then our partner, NVIDIA, who's helped put a lot of this together, Julia, and I don't know if Julia is online. I think she had to leave early. But again, yes. She's here. Hi, Julia. How you doing? Like a big thanks to Julia and her team putting this together with us. This is, from my perspective, has been very successful. We've had 2 hackathons now. We're heading into our 3rd and a workshop. So it's a unique, well, maybe not a unique experience, but certainly an experience that is important to the scientists here, and I think adds value across the organization. So for hackathons, right, our purpose here is to accelerate AI research and HPC codes with the guidance of mentors, right? So mentors are provided through NVIDIA, again, and our partners like Oak Ridge and some other DOE labs have provided a lot of expertise to the folks participating from NOAA and across industry as well in a very collaborative environment. It's a multi-day event, so they typically run a week with some prep, and they're designed to help teams of 3 to 6 developers accelerate their codes on GPUs using program model machine learning frameworks of their choice. And then obviously we talked about mentors, but getting help from those mentors really is impactful to teams. So that also is a big benefit of participating. So the hackathon is open to all the NOAA scientists and their collaborators, right? I think the requirement is that you have a NOAA PI, but the rest of the team could be from collaborative institutions or other partners that we have. Our last event was just a couple weeks ago in August. The link is on the slides there for the event that happened in August, and we're planning a second one in 2022 that'll happen in February, and the calls are open in October, and you'll see it as long as you have a NOAA email address, you'll see that call go out, and we can certainly work to advertise that a little bit wider in the NOAA community. In terms of the success factors, we're looking for active and motivated teams, which we always get, which is great. 3 to 6 members again, and it starts with an application process. So when we open up the call, we're looking to work with folks on their applications, refine them if we need to, but we try to stay engaged throughout the application process. Compute resources, we have cluster access within NOAA, and then NVIDIA and our partners have also provided cluster access to help during the hackathons. We also are planning a boot camp, so there's a NOAA focused boot camp on December 10th. That's a hands-on 1-day course that'll help you learn the basics of GPU computing, AI concepts, particularly as it relates to deep learning. And finally, mentors are the secret sauce, right? So we are building a community or trying to build a community of mentors within NOAA and its partners. So if you're interested, there's a link there to that'll help you, or excuse me, point you in the right direction to become a mentor. I think it's a good opportunity to work with the community, work with your other NOAA scientists to help push the code forward. But there's an opportunity there. There's training involved, and certainly the program we can discuss how we can support that moving forward. And I don't know, Julia, if you're going to talk to these or should I keep going?
Yeah, I can talk through this. Thanks a lot, Frank. So I just wanted to quickly give an overview of the program overall. So we are, all hackathons are under OpenACC org umbrella, where NVIDIA is a member and contributing, Oak Ridge is a member contributing mentors, resources, and helping organize an event. This year, we are going into 25 hackathons so far. So one of them was with NOAA, and one will be next year with NOAA again. So you're welcome to come in and apply for this event. We're always happy to see you at any of this. You're welcome to come to the NOAA, but you're also welcome to come to others if timing works better for you. We always have a GPU resource available. We always have mentors available. We have a mix of HPC and AI application at each event. You usually come to the event. The event goes 4 days over 2 weeks. We assign mentors for the duration of the whole 2 weeks. And what we hear is people really get good results at the end of the event, usually better comparing to if they were doing it on their own in the spare time. We started this event back in 2014. The first one with Oak Ridge National Lab. This is where it all started. So it's their idea to get going, and we as OpenACC organization picked it up and managed to get through. As of now, we have over 400 applications that came through our events, like real codes. Community supporting every single event. We have mentors and computer resources provided by universities, national labs across the globe, really. And in US, our partners that help us with every single event, usually Oak Ridge and NERSC. And please go ahead and check our website with all events. The NOAA Bootcamp and Hackathon is there. And yes, we can go to the next slide. Thanks, Frank. So this is just to reiterate one more time. For hackathons, they're nothing without mentors. And we're really looking for more mentors, more people who can help out and give back to community, or even to start with just a NOAA event, right? So it is a great opportunity to start collaborations, great opportunity to learn what is out there, learn more new technologies, hone your skills, get connections going. So we really encourage you to come and help out. If you believe you're not ready to be a mentor, we have a program, as Frank mentioned. You can go to GPU Hackathon / become a mentor. And we can give you a few labs to walk you through to get into that, to get confidence in GPU programming. And then you can come and mentor as a junior mentor at the hackathon to follow someone who already has experience. So that way you can get into this environment and get going. So either attend a hackathon or be a mentor at the event. We are happy to see you. And the next slide, I think we have one more. Yeah, so usually we have boot camp that leads to a hackathon, and this is exactly what we're doing right now with NOAA. So this is a link to register. So we just opened it up yesterday, December 10th. There will be AI for Science Bootcamp hosted with NOAA. Please, if you're interested to learn more about AI and how it can be applied in simulations, so this is a great way to get going. We will be covering some image classification using AI and data-based simulations as well. So please check it out. It's one day, so we'll be happy to see you. The goal of this event is for you to build confidence in GPU programming, to learn how GPUs can be used in AI. We give you access to the resource. You will be able to use and play with that. We're also going to give you a challenge, some real life example. So one of them is actually based on the NOAA paper of tropical storm identification. So you're going to be using TensorFlow to learn how to apply AI concepts to identify storms. So something like that you will be able to do from scratch on your own after this bootcamp. And then we welcome you to the hackathon. Again, you're coming near, and we will assign you mentors and take really good care of you. We have quite a few people on the call, I think, who already went for the hackathon. I think Douglas is one of them. So he can give you a little bit more information about how it works if you have any questions. In terms of the number of spaces, so the question coming in, if the hackathon is limited, sorry, bootcamp is limited. We do have some limitation. I think we are using our NVIDIA cluster at this point of time, so we're limited to about 80 participants. But it's quite a high number. If we're going to go higher than that, we can figure out how we can get more GPUs to get it going, right? NOAA has some resources. I know you have guys have Amazon resources, so we can figure it out. If there is an interest, there is a willing to learn, we are happy to accommodate that. Okay, and I think that's it on my side, but I don't remember. Yeah. Mm-hmm. Thank you.
All right, thanks, Julia. Just to kind of go back to the GPU resources, if there's a need for it in HPC or in your scientific computing, let us know. We're always open and always happy to receive requirements across the user base. So please let myself know or Bill know, and we're happy to work on refining those requirements and working them into our planning. For GPU resources, Julie mentioned, we do have some resources at the NESC in Fairmont that's attached to our Hera system. And we're working to upgrade, transition those at some point in the future. We are working, again, within the program to see if we can put together a newer GPU test bed, testing things with a limited number of GPUs. So we are working to incorporate that as well. I strongly encourage folks that if you're interested in being a mentor, that's a need that we have within NOAA. Certainly expands your presence in the community, but it also expands your presence within NOAA. And there's a lot of opportunity for development support, not only with GPUs, but generally in ML and AI, and also in HPC. Other programs that you guys might be interested in is the incubator program, which is a yearly program. It's internal to NOAA. The proposal call will come out in the spring of 2020. It's a growing program. We've been doubling. It allows a small amount of funding to go out to groups who are looking at novel technology, new programming methods, new AI or ML methods. When we usually have themes, the themes will come out probably late in the winter time, or later in the winter, or early spring before the call comes out for the actual program. And again, we have the hackathon coming up in February and the boot camp in December. And I see there's a question about how do we apply for the hackathon. So when we put the call out, we'll put a link in there, but we try to, there's a website and some other advertising methods that we use. So you'll see that call come through the normal NOAA channels in the next, as we get close to the winter time. And I think that's it for us.
Thanks, Frank and Julia. And we did invite one team from this year's hackathon, because from the GPU hackathon. Deanna, are you here?
I'm here.
Go ahead to share your result from the plankton automation. I was really impressed by the plankton identification topic that you were talking about.
Wonderful. All right. Well, I can share my screen. Just give me one sec. Oop. There we go. Okay. Can you see that?
Not yet on my end.
Okay. Let's see. Let me try again.
Why? Yes, perfect.
Okay, there we go. Great. Okay, well, hello, my name is Deanna Krauser. I am a zooplankton ecologist at NOAA's Alaska Fisheries Science Center, and this is Plankton Automation, bringing AI and machine learning to zooplankton ecology. So this was our team for the NOAA GPU Hackathon. I believe we may have had the largest team to participate in one of these hackathons. We took networking and resource pooling very seriously for this event, and it ultimately served us well in the end. We had a zooplankton team from Alaska's Fisheries Science Center, the University of Washington, as well as the Prince William Sound Science Center. We had an algorithm team from the Hart Research Institute and Texas A&M, and as well as a data and recruitment team from NOAA and the University of Tasmania. We're still working together and continue to progress made at the hackathon, and hopefully we can publish our findings. So plankton make up the base of the marine food chain, providing essential nutrients to the entire ecosystem. This means we can use them as ecosystem indicators to predict the overall health of our oceans. From a fishery standpoint, they are a critical component of fish diets, and an abundance of fatty zooplankton leads to an abundance of chunky fish. So as scientists, we want to be able to accurately measure zooplankton in order to help us manage our fisheries. You may be wondering, how does one go about collecting these tiny critical critters? Well, believe it or not, we're still collecting them using 19th century technology, where we drag nets through the water and we have humans look over them under a microscope. To be more specific, we have about 10 highly skilled women in Szczecin, Poland that sort through them and report the official counts back to us in Seattle, Washington. You see, the problem with nets are you only get a small sample. It's like looking at a snapshot of section 112, row 3 of the Seattle Seahawks football arena. Knowing how large the arena is, you can kind of make an inference as to how many people are at the game, but you really don't know for sure. Row 3 could be out getting drinks when you took that snapshot. So that means for zooplankton, we can't get the spatial and temporal resolution we need using our current methods of collection. It also takes a lot of time and effort to collect these samples and to look at them. It takes about 1.5 to 2 years for data to become available after collection. And because of this, we have implemented a rapid zooplankton analysis where we quickly look over samples aboard the vessel once collected to kind of get an idea of what's in the water while we await the official counts to come back to us. Unfortunately, not everyone is a professional zooplankton taxonomist like myself, and looking at live moving critters under a microscope aboard a moving vessel is no small feat. Now, when it comes to imaging technology, believe it or not, it's been long applied to zooplankton ecology, both in the laboratory and in the field. In fact, generating high quality image data has become routine, particularly in the laboratory. Unfortunately, difficulties in quality image generation from field applied technologies continue to exist, though improvements are being made here. A leading limitation with using zooplankton images to address ecological questions is still the amount of time necessary to process images into something that resembles net-derived data. And the current available software designed to identify and classify images has yet to significantly reduce that researcher time input and allow for image identification to be a fully automated process, which is the ultimate goal. And this is because large annotated training sets are required to produce images. And these training sets are location specific and they take a long time to produce. And once they are produced, we're still observing substantial misclassification rates. The development of artificial intelligent algorithms to identify zooplankton images would allow significant advances in zooplankton ecology that may be used to address basic science questions in support of ecosystem-based management. So going into this hackathon, our goals were twofold. First, we wanted to develop a workflow to process collected zooplankton images from different in situ camera systems and improve upon an existing AI algorithm that was developed by Dr. Rob Campbell using images collected in Prince William Sound. And second, we wanted to develop a workflow to process collected ex situ plankton images from a highly annotated set of images generated at the Poland Sorting and Identification Center in Szczecin, Poland, and then extract regions of interests or ROIs from the images for classification and size estimation. As for our approach, the plankton group assembled annotated data sets to use as the raw material for algorithm development and training. The coding group then worked to develop an image augmentation module to enhance and supplement the aforementioned annotated images for learning, as well as develop a novel deep learning algorithm based on ResNet to classify the annotated images from the in situ camera systems. The final step in our approach was to then test the model on the NVIDIA GPU cluster using profiler software to evaluate the performance. And then based on model performance and profiler output, modify that code to improve and optimize model performance. During the hackathon, we combined annotated images from 2 camera systems at Prince William Sound and Puget Sound for an initial accuracy of 74.94%. We made a total of 3 modifications to the model during the course of the hackathon. First, we used the image augmentation to bolster the training data set, and this was actually an idea that was proposed by our mentor, James Mott from the University of Wyoming. And then second, we used an image normalization approach to streamline the ability of the algorithm to compare the images. And finally, we developed a multi-stage classifier to further refine individual classes with considerable confusion, which really took our algorithm to the next level. We were able to increase our accuracy on the whole data set from 74.94% to 87.8% after only 15 epochs. And that accuracy has only increased as we continue to develop and expand our annotated training sets. Achieving our second goal was the icing on the cake. This effort was led by our mentor, Ryan Simpson at NVIDIA, who focused on developing a set of code to detect regions of interest, save those ROIs, and then detect their size based on a calibrated micrometer. And this resulting data can be used to facilitate algorithm learning and ultimately expands the use of our newly developed deep learning model. So in conclusion, the hackathon facilitated some major advancements for the world of zooplankton. We walked away with a working algorithm that we are continually trying to expand and perfect. And we have a segmentation script that we can use on really any images collected of zooplankton in the laboratory or out at sea. Moving forward, we have some big plans to implement these new tools like a shipboard algorithm for generating real-time data, meaning we can just snap a picture at a microscope on the vessel and automate the data so no taxonomic experience is needed. And we hope that this will replace our rapid zooplankton analysis. We also hope to increase autonomous technology by equipping a video plankton recorder with our working algorithm to continuously collect images, which will allow us to collect that spatial and temporal data that we've yet to observe after all of these years. So some really, really exciting stuff that I'm thrilled to be a part of.
Thanks, Deanna, which is, again, I really like all those like photos of the planktons, which I have never paid too much attention before because too small. And I would like to bring up Frank and Rob, who to a discussion about how hackathon is important and it can be used for different purposes. Because in this workshop, we have seen hackathon being used as a learning and collaboration opportunity. And for the GPU hackathon, we see as a way to further the developments for the topic that people are already interested in. So let me see if I can highlight Rob. Frank, are you there?
Yes.
Okay. Great. Thanks, Frank. The question I had is, Claire, also I'm not sure if you are still there or not. If you are there, I also would like to bring you up. Because we heard like two different types for hackathon. One is more on the learning and the collaboration building from the joint hackathon with Climate Informatics that bring all like different groups together to form collaborations and learning and training people. And from Frank's and HPC side, which is really bring the resources to the team who can benefit from the resources either from NOAA, from NVIDIA to further the project or development and products. So I just want to ask three of you to share your perspective on how we can all collaborate from NOAA, from communities to make sure this will be an important opportunity or useful opportunity for different groups. So I think maybe I can go with Frank first, if you don't mind.
Sure. So I think, these kind of opportunities, I think, are good for both the ways you described, right? With learning new technology or finding collaborators or sharing methods, right? I mean, they're pretty large events. There's a lot of cross, even on the technology side, you can see a lot of cross discussion between the groups, and they're geared towards that, right? So the groups go off and do what they need to during the day, and at the end of the day, they all kind of come together and talk about what they did that day and how they're progressing, and you see a lot of collaboration across those groups. So I think, these are the types of environments where we can, just like you said, right, bring not only the NOAA community, but the greater community together to kind of collaborate along a bunch of different lines, right? There's a lot of opportunity there. And especially when you're, on the technology side, you're talking about, new methods, whether they be HPC programming methods, whether they be AI methods, or even scientific kind of development methods. Those are all things that we can focus on, right? And kind of those ideas kind of cross-mingle across those groups. So I think they're really good opportunities or at least good platforms for folks to get together and talk about what they're doing and how they can benefit each other.
Thanks, Frank. And Claire, can I ask you to chime in here as the founder of the
Sure. So first, congrats to Doug and all the organizers for doing not one climate informatics hackathon jointly with NOAA, but 3 topics. I think it would be a good idea to include some kind of white paper in whatever proceedings you have about the whole hackathon effort. But it also seems like a lot of the individual challenges, so we saw 3 challenges here, and then some of the NOAA NVIDIA challenges were mentioned, could each publish a paper. So we've seen in the past, not even only winning teams, but other people all helping. So, Duncan is leading the one out of Oxford, and those that got really passionate about that data could actually publish a paper together. And I'm just really excited to see all these international collaborations bringing up. I mean, I think that's the only silver lining of COVID. Last year was the first year we did our Climate Informatics hackathon completely online. That was run by Duncan and Oxford. And you're starting to see people from all over the world really come together for this. But yeah, it would be great to join forces with NVIDIA. Climate Informatics Conference, also organized by Doug, is happening in the springtime, hopefully at NOAA in North Carolina. But if we could kind of merge an NVIDIA GPU challenge with a Climate Informatics hackathon, that would probably be the best of both worlds. We see that industry loves to come to hackathons and meet students. for future internship and job opportunities. And then we've seen now from some of the teams reporting out that we could use more compute. So I think it's win-win, and really just congrats to Doug and all the hackathon organizers of the individual science projects, Natasha, Duncan, and the team from Columbia. Thank you.
Thanks, Claire. And I would like to give the mic to Rob, who is a lead for NOAA Center for AI, to share maybe from our training or another perspective how hackathon is a useful format, or like what's your perspective on that?
Sure, I have the benefit of getting to go last year. First of all, thanks for the other perspectives. And I only wish I had more time to join one of those awesome hackathon teams. I was just sort of watched from the side. So yeah, I would like to say that we had this great plenary. We've had many great plenaries and discussions through this week. And today, for example, we had the integrated AI plenary, and we really discussed deeply how, and also earlier in the week, how bringing together all the right people during the formulation stages of a problem, getting them together. So, for example, I think from Julie's slide sheet for our discussion with her, she mentioned all these different types of experts that are ideally brought together at the same time, like researchers and practitioners, experts in data science and informatics, experts in the earth science, system sciences, and now experts in data science and AI, along with also trustworthy AI. So I just want to say, I think that hackathons are this brilliant format for bringing more of all the right people together. And I forgot to mention risk and decision policy and social scientists. So they would also be included in that group. So I guess what I'd like to say for great, it seems like a really brilliant platform. I think it's great for three angles that I'm thinking about for the NCAI. One, training, just getting that basic 101 that our workforce across NOAA is asking for. They're asking for to get kind of a basic level of fluency for themselves and being available for others as well. Having access to to learn on NOAA scene data, so basically NOAA's data in a cloud environment next to high performance computing, and learn with real NOAA data. That also, the output of that might be awesome labeled training data sets for future use. So I think what it would be cool to explore is your thoughts on bringing a fully integrated team together that could include both the Earth system scientists, which you probably have a great deal of, as well as experts in industry, perhaps, that are experts in AI and ML, and also those at NOAA, along with social scientists. Do you have a thought process on how we could bring a broader group of people together into these hackathons and how they could be mentored, or maybe they would also be mentors? Can I pose that question back?
I think, are you asking me or the other two?
Yeah, the others. Yeah, Frank and right.
So this is a really great point. A lot of feedback we've gotten from past years of climate informatics hackathons is, well, great, but how do you get these messages sort of storified into narratives that can go out to policymakers? So as opposed to actually competing on a hackathon team, if we could involve the social scientists and maybe policymakers with seeing the whole trajectory. So what the challenge problem is, because one thing we're doing is we're curating really important challenge problems for each topic, and then what the results are. So and then maybe the social scientists can sort of have the challenge of how do we get this in front of decision makers and in front of stakeholders. So, they could also sit in on the individual teams. I have a social scientist now interested on AI for the energy transition, who sits in on all our research meetings, observing us because she's an anthropologist. But I think really they would fill this gap of where the rubber meets the road, all this effort and, late nights by the eager people on the teams results in hopefully a publication. But I do believe that the social scientists can really help the rubber meet the road and help get our work out in front of people that can make decisions based on it.
Yeah, so I guess to follow up, this I'm learning here too. So, and that's brilliant, Claire. Thank you for framing that so well for me. Perhaps social scientists could be brought in at the beginning. Maybe they're not going to do the late nights with the hackers, but perhaps coming in at the beginning to help sketch what is the question and what is the challenge being addressed, and how might the output of that modeled effort be presented in a way that the rubber meets the road can happen later, so that when they do go and pursue a publication, we know that there's a full connected path possibly to decision makers and users. What do you think about that? Maybe in the mentorship capacity as one idea.
I think
that's what I was gonna. Oh, go ahead.
I'm just
sorry, Frank, I've got a delay. Go ahead.
I'm just trying to do a time check to make sure that we have time. So Frank, if you want have a closing statement on the topic, and we can move on to our closing plenary in 15 minutes.
Oh, thanks, Douglas.
Sure.
Yeah, please, Frank. Yeah, sorry for going so long.
Oh, no. I'm all that to agree with you and Claire. I think these are the way you're putting it together is really good. And I think that mentor, you just mentioned that. I think that from the technical side too, but I think from the social science and kind of approaching the problem from a holistic approach, I think having the mentorship there would be beneficial, right? So you kind of put the problem in the right context. So I think that's something that we need to work on, as a community. How do we structure this so we have the right mentorship, so the social scientists gets integrated, the technical science folks get integrated, right? And we're not focusing on a technical problem or a scientific problem, but we're looking at it from a holistic perspective.
So one last thought, Doug, and then I also have to jump. I was about to type this in the chat, but we're starting to have so much interest from the domain scientists to run hackathons, right? You had at least 3 applicants and you said yes to all 3. That when we do a competitive call for challenge problems, right, we could require some kind of impact statement or a path to impact outline. So if that's required, then in a crowdsourced way, right, a scientist is incentivized to talk to the social scientists on their campus, and maybe also the AI people in terms of really even how they frame their challenges. So I like Rob's idea of including them from the beginning, and this would be almost a crowdsourced way to do it.
I love your idea. I just want to say that it's great.
Excellent. Thanks, Rob and Claire and Frank, for this really engaging conversation. Unfortunately, we're out of time. So with that, I want to close out by thanking everyone who participated in the hackathon and joining the showcase session to appreciate the hackathon value. So thank you so much.
Thank you, Douglas.
Thank you.
And as a reminder, please join our closing plenary right now, in 10 minutes.